Okay, let's start with capacitance and capacitors. So we've already seen a parallel plate capacitor once, so just remind you of that. So we had a parallel plate like that, and then we'll connect it to a battery. So let's draw a battery. So this is the positive terminal and the negative terminal. So that puts positive charges here and negative charges here. So the electric field is uniform between the plates of the capacitor. So we can say that when the battery is connected, the capacitor charges, let's say current flows. I don't want to talk about current yet, so I'll say that the charges accumulate onto the plates of the capacitor until the potential difference between the plates is equal to the potential difference on the battery. This means the capacitor is fully charged, and so let me put D to be the distance between the capacitor plates, and the electric field between the plates will be E. Okay, so D is the distance between the plates, E is the electric field. So the capacitor is fully charged when the potential difference across the plates is equal to the potential difference of the battery. So I'll redraw this. So we have our battery this way connected here. So this is positive. So electric field goes this way, and the distance between the plates is D. So E is the electric field, and so the potential difference across this capacitor is delta V across the capacitor, and the potential difference across the battery is delta V B. So let's do delta V for battery. So for fully charged capacitor, delta V, so when fully charged, delta VC is equal to delta V battery. So the potential difference across the capacitor is equal to the potential difference of the battery. Recall that we saw earlier that the potential difference across the capacitor is equal to the electric field times the distance between the plates. Okay, so we shall use that. So where D is the plate separation and E is the electric field between the plates. So then we can continue. So we know that, so remember that for a capacitor or for a parallel plate capacitor, E is equal to the charge divided by epsilon naught A, where Q is total charge on the capacitor. So this refers to just the charge on one plate, presuming that the two plates are equal, so they each have the same charge. Charge on the positive plate will be positive Q, charge on the negative plate is negative Q. So we can say that Q is the total charge on the plate, and A is the area of the plates, or area of a plate, basically, assuming that again they are the same geometry. So we can say that using delta V across the capacitor equals E times D, we'll see that E is equal to Q over epsilon naught A. Okay, we'll use that shortly. We shall also realize that when the capacitor is charged, the capacitance, let's say a letter C, is the ratio of the charge Q on the plate and the potential difference of the capacitor. So this is delta VC. So this is the potential difference between the plates. Therefore, we can say that C is equal to the charge over potential difference between the plates. So this is called the capacitance of the capacitor. So the ratio of the charge accumulated to the potential difference between the plates is called the capacitance of the capacitor. Capacitance C is an intrinsic property of a capacitor. It is measured in farads. Farad is letter F, so we can say that 1 farad is equal to 1 coulomb per volt. Okay, so 1 farad is 1 coulomb per volt.
Oh, so what kind of property is it?
It's an intrinsic property. Intrinsic meaning that it is unique to the particular capacitor in question. So if you have a parallel plate capacitor, it has an intrinsic capacitance. If you have a spherical capacitor, it's going to be different. If it's cylindrical, it's going to be different. So it depends upon the capacitor in question. Okay. So it will be different for different capacitors. So with our definition of capacitance above, we see that the total charge accumulated on a capacitor is given by the capacitance multiplied by the potential difference.
Is that 1 coulomb or what?
Yes, that's one coulomb per volt. So Q is the charge on the capacitor plate. Charge is of course proportional to potential difference, and so the constant of proportionality there was the capacitance. So the charge accumulated is equal to the capacitance times the potential difference. So we can identify for a parallel plate capacitor. So we can say, so what is the nature of C, the capacitance, if you like. We can say what is the nature of the capacitance C. So we can say that we know that delta V is equal to E times D, and we also said the capacitance, the electric field E is equal to Q over epsilon naught A. Okay, so based upon that, delta V, we said, E times D. So using C equals Q over delta V across the capacitor, we end up with Q. So C equals Q over delta V. So C, so we have Q over delta V, which is equal to E times D. Since we know E, we can say this is given by Q over E, which is Q times D, and then we have epsilon naught A, like that. So the Q's cancel out, and we should end up with the C equals epsilon naught A over D. So this is the capacitance formula for a parallel plate capacitor. So this is for a parallel plate capacitor. This tells us that the capacitance C for a parallel plate capacitor depends only on area A, the area A between the plates, and the separation D between the plates. Okay, so it depends on the area and the separation between the plates. So if you want to make the capacitance large, you make the plates very large. If you want to also make it large, you make the plates close together. So you make a large plate in terms of area and you get it close together. That increases the capacitance of the capacitor. Questions on that so far? So let's look at the next item there, which is forming a capacitor.
Sorry, what is D again?
What is what?
D?
D is the separation between the plates.
Oh, okay.
And A is the area of each plate. Okay, so we can form the capacitor from any two electrodes. That was the point I was going to make. Okay, any two electrodes next to each other can form a capacitance where C is equal to the charge divided by the potential difference between the two. Okay, so that formula always applies, and we can say that the capacitance depends only on the geometry of the electrodes. And by geometry, that's what I meant by the area between the plates, distance between the plates, and so on. That is the geometry of the electrodes. So if we have a parallel plate capacitor, then C is epsilon naught A over D. That is unique for a parallel plate capacitor. If you have a coaxial cable, it's going to be different. If you have a wire next to a sheet, that's a totally different capacitance, and so on. So any two electrodes, they have their own unique capacitance. So let's look at combinations of capacitors. Combinations of capacitors. We can put capacitors together to form a series of capacitors, or parallel capacitors, or a combination of both. So we can form a series of capacitors, or parallel capacitors, or a combination of parallel and series arrangements. Okay, so let's look first at the parallel arrangements. So we can take a battery and, let me draw the battery this way. So let's say we have a battery like that. We can form capacitors this way. So, I forgot to mention this, the symbol for the electrical symbol for capacitor is just two parallel plates like that. That's what I've been using all along. The battery at the two lines, but one is longer than the other. The capacitor is just two equal lines. So these are two parallel plates next to each other. Okay, so this is, let's call it C1 and C2, and this is delta V for the battery. So when you turn a switch on, then the two capacitors will charge until they become fully charged. Each of them will have their own total charge. Let's call this Q1 and Q2. So the total charge on the capacitor plates is Q, where we shall say Q is equal to Q1 plus Q2. So the total charge is just the sum of the charge on each plate. So we can say that Q1 is equal to C1 delta V, and Q2 is equal to C2 delta V. So we can say the total charge Q is equal to the capacitance, effective capacitance, and the potential difference across the battery. Okay, so if we use that, then we can see that effective capacitance delta V is equal to C1 delta V plus C2 delta V. And so if you just cancel the potentials, then C effective is equal to C1 plus C2. So for capacitors that are arranged in parallel, the effective capacitance is just a sum of the capacitance of each of those capacitors. So for parallel capacitors, C effective, or in some cases C equivalent, is equal to C1 plus C2. So equiv just means equivalent, EFF means effective. I'm using them interchangeably, meaning that the equivalent capacitance is the same as the effective capacitance. So this will also be true if we have n arrangements of capacitors. So if we have n total capacitors arranged in parallel, we shall have C equivalent equals C1 plus C2 plus Cn, like that. So capacitors in parallel just add up. So if we take two capacitors, you put them in parallel to each other. If one is 10 microfarads, the other one is 20, then the total capacitance of the parallel arrangement will be 30 microfarads. Let's do one more before we go, the series capacitor. Hopefully we can do the virtual lab on capacitors today, so that's why I want to finish this series capacitor. So we have a battery again, and we arrange capacitors in series this way. Series just means we are connecting them end to end. So the battery again is delta V, the potential difference. This is C1, C2, and C3. And since the same current flows through the capacitors, they will have the same charge Q, but their potential will be different. So this will be V1, or let's say delta V1. This will be delta V2 and delta V3. So we'll say that delta V is equal to delta V1 plus delta V2 plus delta V3. So delta V1 is a potential drop across capacitor C1 and so on, and delta V2 is potential drop across C2. So we shall say that since we know that Q is equal to C delta V, then delta V is equal to Q over C. So delta V, which is our total capacitor potential difference across the battery, should be equal to the total charge Q divided by the equivalent capacitance, which should be then equal to delta V1, which would be Q1, which would be Q over C1 plus Q over C2 plus Q over C3. So you can cancel the Q's out, and we should end up with the effective capacitance, the equivalent capacitance, which is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And then we shall say that for n series capacitors, the equivalent capacitance, 1 over C equivalent, is equal to 1 over C1 plus 1 over C2 plus 1 over Cn. So when you're adding capacitors in series, you take the inverse of the capacitors and add them. What this means then is that if you have capacitors in series, you are reducing the effective capacitance of the whole combination or the whole group of capacitors. And if you have capacitors in parallel, you are increasing the capacitance. Okay, so we can stop here.